Ackerman, and this is my thermodynamics assignment. Let's get started. So here we have a diagram of the whole problem and with all the variables given and labeled. So here we have the pipe going into the compressor leading into the rigid tank, and these are all the variables that are associated with this problem. So here we have the list of assumptions that were given. So like ideal gas for air, compression is in steady flow, so Mi equals Me, no potential energy, Ve equals 0, steady state, and Mi equals Me, which I already wrote. So this is a list of all the equations that we're going to use, and these are the physical constants backed up by the A1 and A2 tables. So here in A1, we're asked to determine the velocity of the air at the compressor. So here we have we use the ideal gas equation. We use this not the ideal gas, the mass this equation to with the velocity of the mass. We isolate it for the velocity of the mass, and we substitute this variable with the specific volume as given by this formula. We then substitute the specific volume with the ideal gas formula, which would be has all the variables that were given. So now we substitute A of the area of the tube with pi r squared, which is going to transform into all the variables that were given, and we're going to get that velocity is 267.67 meters per second. So the velocity of the mass would be that number. So now for B, we're asked to determine the rate of change, the rate of heat transfer of the compressor in watts. So here the compressor is the system. We're taking the compressor as the system. So we use the first law of thermodynamics where we cancel out both potential energies and VE equals 0. So that's kinetic energy canceled out. And then we actually combine both masses because because at the compressor, Mi equals Me, that was one of the assumptions made. And now we need to find Hi and He, which we use these formulas labeled in the equation that we're given. So Cp equals T1 and Cp equals T2, and then we get these corresponding values. We plug in Hi and He into this formula, and we take the work to be negative because we're adding work into the compressor. And here it's important, we're taking joules and converting it to kilojoules, so it all cancels out with the equation. So we're dividing it by 1000. Here we crunch all the numbers and get Q equals negative 3.64 kilowatts, or we multiply it by 1000 to get into the proper units of watts. So negative 3641 watts. So the heat transfer at the compressor is that number. So C, we're asked to determine the mass of the air after 200 seconds of operation. So here we take the rigid tank as a system. We use the ideal gas equation, and we isolate it for the mass of the tank. We plug in all the numbers that were given. And we make sure that the temperature is in Kelvin, not in Celsius. And then we're given this we're given this 1.754 kilograms. That's the mass two of the tank. Now, Me equals 0 because there's no mass entering the system of the tank. There's only the mass leaving the system of the tank. There's only mass entering. So so this would be the equation that we have plus the mass two of the initial mass of the tank. So after 200 seconds of operation, the final mass of the tank would be 6.754 after 200 seconds of operation. So at D, we're asked to find the pressure of the tank after 200 seconds operation. So we're given, yet again, the ideal gas equation. We isolate it for pressure, and we use the previous known the previous known mass with all the givens that it's on the problem, and we would guess that the final pressure is 385.1 kPa. Finally, we use the first law of thermodynamics to determine the heat transfer uh, to the room. We canceled out work in because no work is being put in, no work is getting outed, and we also cancel that to 0. We Those Q would be equal to this equation, and these are the equations that are equal to theta I and E. And then we're gonna plug them in using the assumption of 200 seconds Mi equals M2 of Mi. So M2 minus M1. So we're going to plug all this in and it's going to simplify to this. Then we're going to substitute the CV of and temperature tank minus CP of temperature 2. We're going to plug in all the known variables, and then we're going to get the Q the temperature would be negative 50, 5,500, no, 554.7